Welcome to the Introduction to Computer Vision course. One of the early successes of deep learning that was widely publicized was Google Brain learning to recognize cats. The link on the slide points to one of the articles about it from 2012. Indeed, computer vision, the field of study that deals with how computers process, analyze, and gain high level understanding from digital images or videos, is one of the most impressive successes of deep learning. Let us consider the most common computer vision tasks. They are classification, the task of determining whether an object from a certain category, such as a dog, is present in the image presented to the computer vision algorithm. Localization, the task of finding a bounding box around a given object in an image, such as a cat. Object detection, a combination of multi-class classification and localization, where it is established that objects belonging to certain classes, such as dogs and cats, are present in an image. Bounding boxes are placed around these objects and labeled with class identifiers. And finally, segmentation, where the outlines of objects in an image are identified. So, how do computers accomplish these tasks? Digital images are represented as numerical data. A grayscale image is nothing but a two-dimensional matrix where each element represents the intensity or brightness of an individual pixel, typically with an integer value between 0, black, and 255, white, and intermediate values represent progressively lighter shades of gray. Similarly, a color image might be represented by three two-dimensional matrices stacked on top of each other. The elements of each of these matrices represent the intensities of base colors, red, green, and blue, for each pixel in the image that combine to give that pixel its apparent color. These pixel intensities can, in principle, serve as inputs for machine learning models that detect specific object categories in an image. Let us look at a classic problem, a very early example of image classification. In this problem, we are asked to train a machine learning model that is able to recognize handwritten digits from 0 to 9. This capability was originally thought to help automate mail sorting by identifying zip codes on envelopes, and today you might find it in ATMs that are able to detect handwritten dollar amounts on deposited checks. To train our model, we will use the classic MNIST. This acronym stands for Modified National Institutes of Standards and Technology dataset. This dataset contains 60,000 labeled training images and 10,000 labeled testing images. All images are grayscale with a black background and a single white digit between 0 and 9. They are square with dimensions of 28 by 28 pixels, and the labels are integers that identify what the digit shown in each image actually is. The naive approach to recognizing digits in such images might be to try and build a fully connected neural network. That is, a neural network in which the value for each neuron in a subsequent layer is calculated by taking a linear combination of the values for all neurons in the previous layer with varying weights, and then applying a nonlinear activation function to it. An example of such a neural network is shown in the slide. As input features, it takes the intensities of all the pixels in the image. For a 28 by 28 pixel grayscale image, there are 784 total pixels with a single intensity value per pixel. Therefore, the input layer has 784 neurons. Their values are combined to calculate the values stored by the neurons in the first hidden layer. The network may have one or more hidden layers with varying numbers of neurons, and typically ReLU activation functions for each hidden layer. The values from all neurons in the final hidden layer are eventually combined to calculate the output from the network. The output layer contains 10 neurons, each corresponding to one of the digits from 0 to 9. The softmax activation function is used for the output layer so that the value for each of its neurons can be interpreted as the probability that the input image shows the corresponding digit. In the example on the slide, if the network is trained well, the value for the neuron in the output layer that corresponds to 8 should be close to 1, and the values for all other neurons should be close to 0. The weight for such a neural network can be trained using a large labeled dataset, such as the MNIST dataset. For a simple classification problem, like identifying handwritten digits in very small grayscale images, such an approach can actually work. However, if we want to identify more classes of more complicated objects in larger images, it quickly becomes impractical for two main reasons. First, the number of pixels in an image quickly increases as the dimensions of the image get larger. Furthermore, for color images, we need to consider three intensities for each pixel that correspond to the three color channels red, green, and blue. Therefore, the number of input features for larger images quickly becomes very large. For a relatively small 600 by 600 pixel color image, there would be over a million input features. Given that we typically want to decrease the number of neurons from layer to layer gradually as we go deeper into a neural network, a very large neural network would be needed if we pursued this approach. Training such a neural network would require a massive dataset, as there would be a great number of weights to train. A second reason why using a fully connected neural network for most computer vision tasks is a bad idea is that there is almost always a good deal of variability in the intensities of individual pixels for objects that belong to the same category. For instance, the digit 8 in the image that is shown on the slide does not have a closed upper loop. If we switched the dark pixels between the two loose ends to bright ones, so as to close the loop, the image would still be an 8. We could also imagine a different tilt in the script of the writer that would lead to yet other pixels in the image showing up as dark or bright, while the image would still be an 8. Or one might change the intensities for all bright pixels from bright white to gray, again, without changing the digits shown. Generally, no individual pixel in an image determines what the object shown in an image is. To account for all possible pixel combinations that correspond to, say, a cat, we would need an unreasonably large training set. For these reasons, computer vision is most successful when the features it uses to recognize an object are characteristic patterns rather than the intensities of individual pixels. Let's say you wanted to recognize the upright head of a cat. All such heads will have certain characteristic features. For instance, the outer edges of a cat's ears are almost vertical lines, and the inner edges of the ears are lines that are tilted at a certain angle, perhaps close to 45 degrees. These lines are connected by the outline of the top of the head, which is nearly horizontal. The outlines of the eyes are almost perfect circles, and the outline of the nose and the mouth forms a recognizable pattern that consists of tilted and vertical lines. The schematic outline on the right consists just of these features, and it would be recognized as a cat by most people. Similarly, digits also consist of recognizable patterns, such as two approximately circular loops on top of one another for an 8. But how do we teach a computer to recognize features like vertical, horizontal, or tilted lines, circles, and so on? Consider an image that consists of a black field on the left and a white field on the right, separated by a vertical boundary. On the slide, each square of the grid overlaid onto this image represents a single pixel. Assume that we have scaled the intensities of individual pixels so that a black pixel has an intensity value of 0 and a white pixel has an intensity value of 1. Now let's create a filter with a size of 3 by 3 pixels, shown by the red box, and overlay it onto the top left corner of the image. Each pixel of the filter is assigned a numerical value. All pixels in the left column have a value of 1. All pixels in the central column have a value of 0, and all pixels in the right column have a value of -1. A convolution operator for this filter with the underlying area of the image is defined as follows. First, we multiply the value for each of the filter's pixels by the intensity value of the underlying image pixel. Then we sum these products for all the pixels of the filter. The result is assigned to be the value of the pixel of a new image that is located under the central pixel of the filter. Now we will shift the filter over the image, pixel by pixel, from left to right, then bring the filter back to the left edge, but move it down by 1 pixel and shift it from the left to the right again, and so on, until we reach the bottom right corner of the filter. For the initial position of the filter, the underlying image pixels for all filter pixels have a value of 0, so the convolution value is 0. The situation doesn't change when we shift the filter by 1 and then by 2 pixels to the right. The second and third panels in the top row, the convolution is still 0. But what happens when the filter overlays the boundary between the black and white regions? The first panel in the second row. Now, the products of the values in the first 2 columns of the filter with the scaled intensities of the underlying black pixels of the image are still 0. But the products of the values in the last column of the filter with the scaled intensities of the underlying white pixels of the image are now -1. Therefore, the convolution for this position of the filter is -3. Similarly, when we move the filter one more step to the right, the second panel in the second row, the convolution is going to also be -3. Then, when we continue moving the filter to the right, and it is entirely on top of the white region of the image, the convolution becomes 0 again. That is because the products of the values in the first column of the filter with the scaled intensities of the underlying white pixels of the image are 1, and there are 3 of them. The products of the values in the last column of the filter with the scaled intensities of the underlying white pixels of the image are -1, and there are also 3 of them. And of course, the products of the values in the middle column of the filter with the scaled intensities of the underlying white pixels of the image are 0. When we sum up these numbers, the products for the first and last column cancel each other out. So what we find is that we get a non-zero value for the convolution when the filter overlays the boundary between the black and white regions. And we get a zero value for the convolution when it does not. If we run the filter over the entire image, as described earlier, assigning the result of each convolution to the pixel of a new image that is located under the central pixel of the filter, we get the result that is shown in the bottom right corner of the slide. The values of the pixels on either side of the boundary in the original image are non-zero, and the values of all other pixels are zero. Thus, the filter we designed is a vertical edge filter. Notice also that due to the 3 by 3 size of the filter, its center can't be placed over pixels on the edges of the original image, with the entire filter still overlaying the original image. Consequently, no values can be assigned to those pixels in the transformed image. So, in that image, a boundary with a width of white pixel is lost on all sides. Normally, that is not a problem, as we rarely look for features that are located directly on the edge of an image. However, shortly we will see how to avoid losing pixels at the edges if necessary. A vertical edge filter can be used for detecting vertical boundaries between regions of different shades. Similarly, a variety of filters can be constructed for recognizing a wide variety of patterns. However, constructing such filters manually and hard coding them into our application would be tedious. It would require us to figure out what specific patterns we need to be looking for each category of objects that we want to detect. And we have done that with the head of the cat. A much simpler and more powerful approach that is used in computer vision is initializing filters with random weights and then training the weights to automatically learn what patterns are prevalent in the data and characteristic of the target object category for an image. This modification of the approach is what separates old school image analysis, where algorithms are built to look for specific patterns in images, from image analysis that uses machine learning. Let us discuss some parameters of filters and convolutions. In the example that we discussed earlier, our filter had dimensions of 3 by 3 pixels. However, other dimensions of a filter can also be selected. Filters are typically square with dimensions of 5 by 5 pixels, 7 by 7 pixels, or even larger, being pretty common in computer vision applications. Filters with dimensions of 1 by 1 pixel that overlay a single pixel of an underlying image are also used. The number of pixels along a side of a filter is referred to as the kernel size. Odd kernel sizes are typically used for convolutions, as they have a central pixel that defines the location to which the result of the convolution is assigned in the transformed image. As we have seen, pixels at the edge of an image are lost when running convolutional filters of size larger than 1 by 1 pixel over an image, because the center of the filter can't be placed over those pixels with the entire filter overlaying the image. If we would like to avoid losing pixels at the edges of the image, a possible solution is to simply pad the original image at its boundaries by one or more pixels. Convolutions performed without padding are referred to as valid convolutions, and convolutions performed on images that have been padded so as the transformed image is the same size as the original image are referred to as same convolutions. The term padding is used to denote the parameter that defines how many pixels have been added at the boundaries of the original image on every side. In our examples so far, we have always shifted a filter by a single pixel to the right or downwards as we ran it across the original image. However, there is nothing to prevent us from shifting a filter by any other number of pixels in each step. The parameter that defines the number of pixels by which a filter is shifted in each step is called the stride. If the stride is more than 1 pixel, then we speak of a strided convolution. Using larger stride values is computationally efficient, as fewer convolutions need to be performed as we scan a filter over an image. However, it reduces the resolution of the transformed image. Furthermore, in order not to lose information about any of the pixels in an image, stride values that are no greater than the filter kernel size are almost always used. When building computer vision applications, it is important to keep track of how transformations change the size of an image. Before any convolutions are performed, images are often rescaled to be square. If we start with a square image, then the size of a convolved image produced from it is given by the formula that is shown in the slide. Here, the original image has a size of n by n pixels. P is the padding, F the kernel size, and S the stride that we used for the convolution. The brackets with an angle at the bottom denote rounding down to the nearest integer, known as the floor function. For example, if we start with a 28 by 28 pixel image, such as the ones in the MNIST dataset, and perform convolutions with a filter of kernel size 3, a stride of 1, and no padding, we will get a 26 by 26 pixel image. N is 28, P is 0, F is 3, and S is 1. Thus, we have lost 1 pixel on each side of the image. Since we have not used any padding in the terminology that we introduced in the previous slide, this is a valid convolution. Padding by 1 pixel, N is 28, P is 1, F is 3, and S is 1, would avoid losing any pixels. The resulting image would have dimensions of 28 by 28 pixels, same as the original image, and in the terminology that we introduced in the previous slide, this is a same convolution. Before we talk about how filters and convolutions can help with developing machine learning tools for computer vision, we need to discuss one other topic, 3D convolutions. Let's say we have a color rather than a grayscale image. As we said earlier, each pixel in a color image can be represented by the intensities of several color channels, for instance 3, red, green, and blue. We can define three-dimensional filters with the number of channels in the filter equal to the number of channels in the image. We can place this filter over the image. Then we can perform a convolution of each channel of the filter with the corresponding channel in the image. These will be regular 2D convolutions. Finally, we will add together the results of the convolutions for individual channels to get a single number, the result of the 3D convolution. If we shift the filter over the image in the same way as we have done for grayscale images, from left to right and from top to bottom, then the result of a 3D convolution of the original image with the filter will be a 2D image or channel. Note that the number of channels in the filter is the same as the number of channels in the image, and we are not shifting the filter across channels. Each channel of the filter is always overlaid over the same channel in the original image. The number of channels in the original image need not be limited to 3. 3D convolutions are used to process color images, but as we will see shortly, they have other important applications in computer vision as well. Convolutional neural networks, or CNNs, are the current state of the art for computer vision tasks. A basic block of a convolutional neural network is a convolutional layer that is constructed as follows. First, we take several filters with the same dimensions and with the same number of channels that matches the number of channels in the image that they will be applied to. We will denote the number of filters that we use as M. Then we run each filter over the original image, as we discussed in the previous slide, performing a convolution of the image with that filter. The convolution of the image with each of the filters results in a 2D channel. We can optionally add a constant bias to the intensity of each pixel in the resulting convolved image. This bias need not be the same for all filters. We apply a nonlinear activation function, for instance ReLU, to the intensity of each pixel in the convolved image, and then we stack the resulting images from all M filters that have been used on top of each other to get a new image with M channels. In a convolutional neural network, multiple convolutional layers can be used in sequence, along with certain other layer types, on one of which we will discuss shortly. The output from a preceding layer is then used as the input for a subsequent layer. Let's try to understand what the convolutional layers in the CNN accomplish. As we have seen earlier, each of the M filters that we use to construct the convolutional layer can be trained to recognize a specific pattern in the image. Any number of filters can be used, recognizing a variety of different patterns. Using M filters in a convolutional layer results in an image with M channels. Each of these channels then contains information about a specific type of pattern. The image that results from one convolutional layer can be used as input for the next convolutional layer. Constructing it will require using filters that have M channels, matching the number of channels in the input image for that layer. Each subsequent convolutional layer will detect higher level, more complex patterns by combining the patterns that the previous convolutional layer had detected. For instance, if we consider the schematic on the right, the first layer in a CNN might detect basic features like segments of straight edges with various orientations or small circles. The second layer in a CNN might combine those basic features into more complex ones, like eyes or noses. The third layer might combine these more complex features into human faces or parts thereof. Note that we don't explicitly tell the layers of a CNN what features they should be looking for. The filters for each layer are initialized with random weights. The weights are adjusted in the process of training a CNN on images of specific object categories, in this case, faces. This training is performed in a way that is very similar to that for fully connected neural networks. Apart from convolutional layers, nearly all CNNs that are used in computer vision applications contain pooling layers. The two most common types of pooling layers are max pooling and average pooling. For both types of pooling, a filter with kernel size f is placed over an area of the image. For max pooling, the maximum intensity value among the pixels of the underlying image that the filter covers is the result of the pooling. For average pooling, the average intensity value over all the pixels that the filter covers is the result of the pooling. The filter is then shifted over the image with a stride of S pixels. If the image has multiple channels, then pooling is performed separately for each channel. Therefore, the output image for a pooling layer has the same number of channels as the input image for that layer. Max pooling is by far the most common type of pooling that is used in computer vision applications, as it emphasizes features in the original image by selecting the pixels with the highest intensity in a small region of an image. However, you will occasionally see average pooling used as well. The purpose of pooling layers is to reduce the image dimensionality as we pass data through a convolutional neural network. Commonly, a kernel size of 2 and a stride of 2 are used in pooling layers, so that the output image dimensions for them are approximately 2 times smaller than the input image dimensions. Because all that pooling layer does is selecting the maximum or calculating the average over the intensities of a few pixels, there are no weights to fit for pooling layers. As we said earlier, pooling, particularly max pooling layers, might emphasize pattern in the input image, but unlike convolutional layers, they do not detect new features. Using a pooling layer with a kernel size and stride of more than 1 pixel leads to some loss in the image resolution. But this is not a problem because the purpose of pooling layers is reducing data dimensionality, and because while resolution is lost, prominent features are emphasized in the image. We now know enough to build a simple convolutional neural network for digit recognition. Our network is going to take 28 by 28 pixel grayscale images of digits from the MNIST dataset as input. In the first convolutional layer, we will use 32 two-dimensional filters with a kernel size of 3, and we will use padding of 1 pixel and a stride of 1 pixel to produce a same convolution. The nonlinear activation function used for this layer will be ReLU. The output of the first convolutional layer will be an image with dimensions of 28 by 28 pixels, as this is a same convolution, and 32 channels, because we have used 32 filters. This image will be used as input for the first max pooling layer, with a kernel size of 2 and a stride of 2. The output of this pooling layer will be an image with dimensions of 14 by 14 pixels and the same number of channels as for the input image for this layer, 32. The output from the first max pooling layer will then be passed as input to the second convolutional layer. For this layer, we will use 64 three-dimensional filters with a kernel size of 3 and 32 channels, the same as the number of channels in the input image for the layer. We will use a padding of 1 pixel and a stride of 1 pixel to produce a same convolution. The nonlinear activation function used for this convolutional layer will again be ReLU. The output of this convolutional layer will be an image with dimensions of 14 by 14 pixels, same convolution, and 64 channels because we have used 64 filters. This image will be used as input for the second max pooling layer, with a kernel size of 2 and a stride of 2. The output of this pooling layer will be an image with dimensions of 7 by 7 pixels and the same number of channels as for the input image for this layer, 64. At this point, we will flatten our image. That is, write out the values for all of its pixels in all of its channels sequentially as a column vector. For instance, starting with the top left pixel in the topmost layer, then moving left to right, then top to bottom within a layer before moving on to the next layer. The resulting column vector will have 64 times 7 times 7, that is 3136 elements. This vector will now be passed as input to a fully connected part of our convolutional neural network. This part of the CNN will use information about the relatively high-level patterns in our data identified by the preceding convolutional layers to identify digits from 0 to 9. As we already said, its input layer takes 3136 input values and thus has 3136 neurons. We will also include one hidden layer with 128 neurons and a ReLU activation function. The output layer will have 10 neurons, one corresponding to each digit from 0 to 9, with a softmax activation function so that the values for these neurons can be interpreted as probabilities that the input image shows the corresponding digit. In the next lesson, we will implement the CNN in PyTorch and evaluate its performance.